It's my pleasure to introduce our next speaker, Craig Russin. He's the Chief Technology Officer for Medical Informatics Corporation. I'm leaving it at that. So, with that, we'll get your slides up. And we'll get it there. And there's a pointer here if you need one. Okay. All yours.
Perfect. Well, thank you very much. Thanks for having me here. I am Craig Russin. I am the Chief Technology Officer of Medical Informatics Corporation, a company that I co-founded. And I'm also an assistant professor in the Department of Pediatric Cardiology at Texas Children's Hospital, as well as an adjunct faculty here at Rice in the Department of Computational Applied Math. So I'm actually quite an odd duck, actually. I am the only engineer in a clinical department of pediatric cardiology at TCH. And what that means is that I have the pleasure of seeing where all of the challenges are in a clinical environment, right? A clinical environment like this. So, show of hands, who here has been to an ICU? Wow, that's actually a significant number. Not surprising, given the proximity to our medical center. But it is a harrowing experience, right? If you had to have been exposed to this environment. There are a number of decisions that need to be made quite rapidly, often with the lack of information. And I know, and I'm using the word information in particular because there's actually a tremendous amount of data that's being generated. It's just not very well translated into useful information. And one of the largest components of whether or not you have a good outcome in this environment is surveillance, right? It turns out the more eyeballs that you have looking at a patient, the better their outcome is going to be. So if you have more nurses, if you have more physician time, these are measures that have been correlated to better outcomes, right? So one of the most useful tools in patient surveillance is the patient monitor, right? You probably see these on TV. They beep like crazy, and they generate a fairly significant amount of data. Maybe not Google or internet scale, but for a hospital, this is a tremendous amount of data. Each monitor generates approximately 300 megabytes of data a day, right? So when you talk about that in terms of comparing this data to genetic data, right? You're talking about a week's worth of time. So if you're in an ICU for a week, you generally generate about the same amount of data as your genome, right? And this also means that you have more data coming from this monitor than actually is going into your EMR, right? So the data set that we have at TCH far exceeds the data set that TCH actually has in their EMR. Now, what's interesting about these devices is that they have been relatively constant over a very long period of time in terms of their functionality. So what you see here is an ECG in 1930 from a strip chart, right? So just a piece of paper, a little needle that goes and traces out the rhythm of your heart. And you can see the same ECG in a CRT tube, and now you can see the same ECGs coming in through an LCD monitor. So literally the biggest thing in patient monitoring that has changed is the display media on which data is presented to you. I kid you not. In the same period of time, obviously, computational power has increased by 7 orders of magnitude. So where is it, right? Where is it going? Well, that's what my research and the startup company that I've co-founded is trying to bring to bear, right? We want to take, because ultimately patient monitoring is about pattern recognition, right? Looking at the patterns that are associated with precursors of deterioration. Because you don't want to catch the arrest by having a page on your phone saying, oh, my patient arrested, right? I need to go run. I want to know an hour or a day prior to when that event occurs so that I can intercede, right? Or a physician can intercede before symptoms become life-threatening. And the problem is that, and this is just a pattern recognition problem, and physicians, and there's a tremendous amount of literature out there in terms of what these sort of patterns look like. The problem is that we can't sit a human and have that human look at that monitor 24/7, 365, right? Which means that we need to have a computer do it. And this is a brand new thing in terms of hospital, well, not brand new, but relatively new in terms of hospital operations. So the goal is that we want to take this data that's continuously generated from our patients And we want to analyze it in real time in order to have some continuous measure of risk of some bad event, right? That bad event could be an arrest, or it could be sepsis, or it could be ventilator-associated pneumonia, you name it. There's a number of different risk factors that any one particular patient can have. And so when we talk about real-time analysis, it's not just kind of one algorithm to rule them all, right? It's a suite of algorithms, hundreds of little algorithms that are specifically engineered in order to identify risks, the precursor or the patterns that are associated with particular risks. And this is not a new idea, right? I'm not a physician, but I can tell that Captain Kirk is not having a good day. Okay, so the real question is, how do we get here? How do we get from our nice strip charts that are on LCD screens now to something like what we see on TV, almost 60 years ago? Well, this is where medical informatics comes in. We have developed a product called SickBay. And yes, we did make this. That is the actual name of our product. And as you'll see in the next slide, we're very proud that we got the FDA to recognize SickBay as a Class 2 medical device. And what SickBay does is it performs a very important function. It takes all of the data from bedside monitors, ventilators, near-infrared devices, pumps, nurse call, alarm notifications, anything that goes in and out of an EMR, and it provides the ability to process all of that information in real time, to provide new and useful metrics to users, like physicians, to middleware systems so that they can actually send messages back and forth, and also to the EMR. Right, so it kind of acts like the CPU of a hospital. Like I said, FDA-cleared Class 2 medical device. And so I'm going to talk to you about one of the example applications that we've built for SickBay, in particular for one of the critical populations that's extremely important to Texas Children's Hospital. And these are kids with what's called single ventricle physiology. So I'm going to take a bet here that 99.99% of you guys have four chambers to your heart. These kids have 3. Right? In this particular scenario, one of the ventricles is underdeveloped to the point where it doesn't work anymore. And these children have to go through a series of 3 surgeries very early on in life in order to survive. 40 years ago, the mortality was, 50 years ago, the mortality was 100%. You did not survive from this condition. Over the course of the next, 20 or 30 years, the surgical techniques have gotten so good that now their survival rate is more like 85%. So still 15% mortality, but has dramatically improved. So it turns out that the vast majority of deaths in these children occur between their first and second stage surgery. So between 5 days of life and maybe 6 to 9 months of life. And in this system, or at this time, these children have what's called a parallel circulation. So basic physiology is that your heart pumps blood to your body, then back to the heart, and then to the lungs, and then back to the heart. These kids have one pump. So the blood goes from the heart, gets split, a percentage goes to the body, a percentage goes to the lungs, and then it comes back, and it mixes. It's this mixing that causes hemodynamic instability within these kids, which leads to various types of deterioration. And so the majority of deaths in these kids are due to some sort of arrest, either a cardiac arrest or a respiratory arrest. So they either stop breathing or their heart stops. And so the question that we had was, is there a precursor to this? This doesn't just happen in a second, right? What is the physiologic pattern that the patient is providing us? What information are they providing us that we can leverage in order to anticipate these events so that we can give some sort of intervention to prevent these arrests from occurring and thereby improve their mortality? Okay, so this is where SickBay comes in, right? These children are in the hospital for a tremendous period of time, oftentimes 9 months at TCH. And so we have to go, and we never know when any of these arrests are going to occur, so we literally just have to monitor them all continuously. And that's what SickBay does. We started data collection on January 1st, 2013, and we've been monitoring 24/7, 365 for almost 250 beds in the hospital. That's about half of the monitors, right? We've collected about 520 bed years of data, which is about 40 terabytes. So it's one of the largest known and most complete physiologic histories of children in the world. We have 500,000 unique patients. We have 40 million labs, 30 million meds, and over 60 million alarms. Right? So this is a fantastic data set in order to develop predictive algorithms, right? Because it's literally all of the high-resolution data coming from every monitor device that these kids were attached to. So we did some basic machine learning. And this isn't sexy. It's simply feature detection, or it's simply a couple of filters, some feature extraction, and then a very simple logistic regression model, right? You know, I'm not a machine learning expert by training, but basic data modeling is definitely doable. So just using a simple system like this, what we're able to do is predict the onset of these events with a ROC area of about 0.91 and a positive and a diagnostic odds ratio of about 180, right? And this is 1 to 2 hours before the event occurs. So in this time period, with this level of event recognition, we suddenly have the ability to give a physician an early warning notice that an event is imminent, right? What that means is that instead of having the physician have to examine data like this, which is the heart rate, the SpO2, and the respiratory rate of one of these kids, about 3 hours before the event, instead of having them have to continuously watch this vital sign data, we can provide them with a real-time risk index that's calculated continuously from the bedside monitoring data, right? What you see is that in this particular case, right, about 3 hours prior to the deterioration, the index is between like 1 and 5, and it's all scaled to the average risk of having an arrest in that population. So 1 is that their average risk, 2 is twice the average risk, 3 is 3 times the average risk. So if you go from 1 to 4, that's okay. Now you're 10. Half hour before the event, you're at 19. And then 15 minutes before your event, you're at 35, right? It provides a far easier way to estimate the relative risk of when these events occur. Okay. So this was a great result, right? We had papers, we got funding from the American Heart Association and the National Institute of Health. We were invited to TED Med as one of their Hive innovation companies for 2016. This is great. But now what, right? We can't just stop at the papers. We can't stop at our grants, right? We have to have the ability to take these algorithms that either we build or that you guys build and bring them into the clinical environment. Because without that, it's just another paper, right? It doesn't have the impact that it should. And that's also where SickBay comes in, right? The reason why this platform is so powerful is because we bridge that gap between what physicians are used to, looking at the traditional monitor that they're seeing. This is all web-based, all real-time. But we bridge this gap because we can present all of the real-time web data that they're used to and combine it with new and novel functionality. So we can literally assign algorithms to watch over the data streams of patients, and we can do this at scale. So instead of having them look at the traditional monitor that's been around for 70 years, we can now build a dedicated virtual monitor that is specifically designed to elucidate what the risk is of arrest for this particular population. So this is our risk index as calculated over time over the last 12 hours. Currently, this is obviously an example. And then all the other supporting information that the physician needs in order to confirm that this is indeed an impending arrest and trying to figure out what to do about it, right, because different types of events require different interventions, is automatically provided, right? And since these algorithms are stood up on a patient-by-patient basis, they're persistent. They're processing in the background in the data center of TCH, even if Every browser in the hospital is closed. Even if nobody's looking at sickbay, the system is still processing, watching over those patients in our ICU. And when it detects that there is a high risk of arrest, it can actually send a text message out to the providers via their mobile devices that says imminent catastrophic event detected, with a hyperlink back to the monitor in order for them to make a decision about how to act. Right? So, as I said, this platform provides a unique opportunity for researchers and data scientists in order to improve patient care, because it normalizes all of the complexities that occur in a clinical environment, right? So no matter your monitor vendor, EMR, or you name it, right, all of that stuff gets normalized into a time-synchronized and consistent data set that you can then leverage whatever algorithms that you want in order to develop new and novel modalities to monitor patients, right? So we support open data formats. We have a web-based MATLAB, C-based and Java-based API. We even have a standard development kit, because we realized that, the part of the problem in this field was that all of the data that was generated by these monitors was simply lost because it just wasn't recorded, right? The vendors locked their data formats and nobody was able to get access to it, at least not at the scale that's required in order to make these sort of developments occur. So we want to change that paradigm. We want to make this data available so that third parties can leverage it in order to build algorithms to improve the way that patients are monitored, right? So the example is, your app here, right? Because that's, at the end of the day, that's what it's all about. It's about making this environment more safe by providing additional layers of surveillance on top of the data that is already being generated. So with that, I'd love to take any questions, and thanks so much to both my colleagues at MIC and Texas Children's.
I think we have a hands-down winner for finishing early and getting this whole message across. Question there.
How customizable is your sick day to avoid false alarms? Physiological data is different from patient to patient and from patient population. Like this case, average to adults. Is it highly customizable and can avoid false alarms?
So,
can you repeat the question?
Yeah, so the question is, how customizable is sickbay to avoid false alarms? And there's kind of two answers to that. The platform itself is designed to simply provide the algorithm with all the data that's available, right? Because what's noise to one algorithm may actually be signal to another. And to have the platform make that decision is not really correct, right? It should be up to the developer of the algorithm to do all of the filtering and all of the signal processing in order to make that determination. So what the platform provides is a normalization layer. So you don't have, as a developer, you don't have to worry about whether you're getting data from a GE monitor, or a Philips monitor, or a Draeger, or whatever, right? You have a consistent view onto the data. Now, if you want to filter out, the R wave of the ECG because it's not useful to you, then you can do that with whatever environment that you want to operate in. So if you're a C programmer and you already have your code written for that sort of signal processing, you can simply bind it to our API and then away you go, right? So it really gives the developer the flexibility to do what they need to do for the problem that they're trying to solve.
Okay. So we have one here.
At what interval of time are you guys storing your data?
So we store the data at the native resolution that we receive it. So ECGs at 240 hertz, blood pressure waves at 120 hertz, SpO2 at 60. Most vital signs are between one sample every second or one sample every 2 seconds. It depends upon the waves, but generally speaking, it's between one sample a second for low-res vital signs, and then hundreds of samples a second for all the waveforms.
Here.
What are your plans to share this technology outside of the Children's Health Hospital and Baylor College of Medicine?
What's the plan to share the technology?
Yes. How are we going to share the technology? So MIC is a for-profit company. If you have a hospital, we'd love to talk to you. The other idea is that if you have several hospitals that have sickbay, And we find, and for example, if there's a critical event that a critical safety event that occurs at one of them, wouldn't it be great if you could take that knowledge from one hospital and immediately translate it into all others? That's the type of network that we're trying to build, where we can take these rare occurrences and build algorithms to identify them, and then automatically ship them out everywhere so that the entire network improves, right? So that's the whole idea. So the more hospitals that we get on board, the more data we collect, the larger the data set, the better algorithms that we write, the safer everyone becomes.
One question from the back here, and then you. Way in the back.
Do you foresee that you'll be able to do this in the cloud, or is there too much pushback?
Okay, so the question is, can we do this in the cloud? That is a political limitation at this standpoint, not a technical limitation. The politics are such that hospitals, or at least most hospitals, are not yet comfortable pushing any data that has PHI, so protected health information, to a cloud-based infrastructure, even though Amazon has HIPAA-compliant architecture. And the reason is very simple. They are responsible for it, right? And so if they're responsible for it, they're going to try to protect it as best they can, which means limiting access, right? Because if no one has access to any data, then the data is never going to get out there, right? I think the more, but that actually is starting to change now. So there are a couple of instances where hospitals are now starting to go to the cloud for things like patient engagement, because they see that kind of as a bridge. Make sure that you come in for your appointments or scheduling or stuff like that. But I think that in terms, and I think as that evolves, I think you'll find more and more applications, being politically cloud ready. I just don't think patient monitoring is quite there yet. I think that's going to be an internal capability inside the hospital for a while.
One final question over here.
Do you have before and after data for mortality rates?
We're actually generating that right now. So that was what the grants are for.
So in closing, as a moderator, I have one question. So you said your app here. Does that mean you're inviting for a hackathon?
We actually have plans to support one. So if Rice University is interested in doing that, we can
talk.
provide the infrastructure.
Let's talk. Join me in thanking our speaker again.